this, we're assuming this, that this language is decidable. Therefore, there's a Turing machine that decides this language. Okay. Now, from that, we're going to use that to construct another Turing machine that will decide this one. Okay. So, in other words, we're going to solve this problem, problem A, by using the solution to problem B. In other words, the Turing machine that decides this. We're going to use the Turing machine that decides this language as a part of the Turing machine that decides this language. Okay? That's the broad strategy. And if we can do that, if we can actually prove then that if this is decidable, then this becomes decidable, then since we know that this is undecidable, therefore it's basically just Moden's tolerance, right? If A then B, but not B, therefore not A, right? That's effectively what's going on. Alright, so okay, so let's start with this. Now we're moving on. So let's find a Turing machine that does decide that. Okay. So let's call now it's not an ordinary Turing machine. It's an LBA, right? It's a finite length type Turing machine. It's an LBA, a linear. What does it stand for again? Bounded automaton, right? Bounded in the sense limited, constrained. Alright, so what we're going to do is we're going to construct, so it'll be a proof by construction, partly. We're going to construct a Turing machine, an LBA type Turing machine, call it B, and test if its language is the empty language. Okay, we'll construct this particular LBA that decides this language, okay, and using this Turing machine B that decides this language, that will help us, that will enable us to decide this language. And we'll use this machine B as a part, as a component, to decide this language. And okay, so that's the next step in the chain of reasoning. Okay, I hope you're with me so far. If not, rewind. Alright. Okay, so if we have this machine and its language, corresponding to that machine, we can test whether that language is the empty language. Right? So what does B actually do? Using this B, we can use that to build a Turing machine, another Turing machine, a bigger one that uses this as a component, if you like, and we'll use this bigger Turing machine to decide this language. So if there is a Turing machine B that decides this language, then we can use it to create a larger Turing machine that will decide this language. Okay. All right. Now, okay. So if this it's got here language B. This is now machine. Sipser really mixes up the languages and the problems. Okay, so now oh, hold on, no, it's okay. So the language that this machine is going to recognize, we're asserting, and we'll justify it later. So, now it's a Turing machine, so we can talk about the language of that machine, L of B. Well, what is the language of B? Now, what does that mean, L of B? Well, it's all the strings that machine B recognizes. Okay. Well, what are those strings? Well, we're going to construct a B such that this Turing machine, or LBA Turing machine, B, recognizes, the strings that it recognizes, they are all the accepting computation histories. Okay? For when this machine M, this M, is it an LBA? Yes, I assume this M is an LBA. Okay, so in other words, this machine B that we're going to construct, that decides this language here, the strings that it accepts are, and we build it that way, right? We build it this way. So the language that this machine B that decides this language accepts, they're all the accepting computation histories of this machine LBA on when string W is input. Okay. And you may say, now wait a minute, didn't we say last board that there's at most one such accepting computation history for a given machine and a given string? And that's the point. That's the point. Okay. Oh, by the way, an implicit assumption, again, part of the reasoning, we are assuming the Turing machines in this discussion are all deterministic. Okay? So you'll just go from one configuration to the next deterministically. So if you're in a given configuration, then the next configuration will be determined. There's no doubt. There'll just be one following or one next configuration. Okay, we're talking deterministic machines. If you want to go into indeterminism, it'll complicate the argument even more. But it can be done, I assume. Sipser doesn't even mention it. It just says we're in the context of the machines all being deterministic. Okay, so assume that. All right. So an accepting computation history for this machine with this string, there'll be at most one of them. Okay, and that's a consequence of the determinism of the Turing machine M. Now, why do you say at most one? Well, you could have the computation history could be looping, right? It's a possibility. So for your M and your W, this string going in W might cause this particular machine M to loop, right? It's possible, and therefore no accepting string. So it's either there's one accepting computation history, or there's none. Right? At most one. Okay. So in other words, the language that this B is going to recognize will have at most one member. Okay? That follow? You follow that reasoning? Okay. Another link in the chain. Okay. All right. Now from that, okay. So we have this machine B. Now think a moment. So this LBA here, if it accepts this string W, okay. Therefore, this machine for this string has an accepting an accepting computation history, right? By definition. So if M accepts W, there is one accepting computation history, by definition. The final state of the computation, the final configuration, includes a state that is an accept state. Okay, we did that previous board, the very definition of an accepting computation history. Right? So if M accepts W, the language, this B recognized, it will contain one string. Okay, follow that? And therefore it's not the empty string, right? Because it's 1 is not 0. Okay. Okay. Now, if M does not accept W, that's another possibility. Then the language that this one's recognizing, well, it will be equal to the empty set, right? Because the language B recognizes is at most has one member, at most, right? So it's either 0 or 1. Now, if M does not accept W, so that therefore, well, there are two possibilities. One is the final state includes the final configuration. In other words, it halted. The state is a reject state. That's the possibility. And the other possibility is it just loops. Okay. So if M doesn't accept W, well, then language B recognizes is the empty set. Okay. So in other words, using this machine, this Turing machine B, allows us to decide ATM, if you think about it, right? Okay. Because we just look to see the size of the language for B, and if it's 0, then we know that the machine LBA did not accept W, right? So it rejected. We know that. Okay. And the other way, if the size of the language B is 1, so it's either 0 or 1. Well, if it's 1, therefore it's not 0. Okay. And if that happens, well, we know that M, the LBA, accepted W. So either way, we know that M will either accept or reject. And that, by definition, means that this machine